Or how we move between different aspects of motion using two mathematical tools, the gradient and the area. Think of displacement, velocity, and acceleration as floors in a building. To move downward from displacement to velocity, we find the gradient, which gives us the rate of change. Going further down, we find the gradient of velocity, which leads us to acceleration. On the way back up, we use the area, or accumulation, to move from acceleration back to velocity and from velocity back to displacement. This process helps us understand motion by shifting between these dimensions in a structured way, like riding an elevator between floors. This graph shows how an object's displacement changes over time, giving us a clear picture of its movement. Initially, the object moves away quickly, which is reflected by the steep upward curve. Then, it reaches a point where it stops moving, meaning its velocity is zero. After that, the object starts moving back, passing its original starting point, which we see as the downward curve crossing below the time axis. This shape helps us understand the full journey of the object relative to where it began. Looking at this graph of position versus time, we see how velocity is indicated by the slope or gradient of the line. At first, the line slopes upward, which means the object is moving forward with a positive, constant velocity. Then the line flattens out, showing a zero gradient, which tells us the object has stopped and remained stationary for a period of time. Finally, the line slopes downward, indicating a negative velocity as the object moves back toward its starting point. This pattern clearly shows how the gradient of a displacement time graph reveals changes in the velocity of the object. We can see that the average speed over the full 10 seconds is found by calculating the gradient of the straight line from the starting point at 0 seconds and 0 meters to the end point at 10 seconds and 200 meters. This gives an average speed of 20 meters per second. To estimate the speed at a specific moment, such as after 6.5 seconds, we draw a tangent to the curve at that point. By calculating the gradient of this tangent line, which connects the points at 4 and 9 seconds on the curve, we arrive at an estimated speed of 24 meters per second at 6.5 seconds. This shows how the speed is increasing over time, as expected in a scenario where acceleration occurs. When analyzing a velocity time graph, the total displacement can be found by calculating the area under the curve. This graph shows velocity increasing linearly over time, creating a triangular shape. To find the total displacement, we divide the area into simple geometric shapes like rectangles and triangles, then apply standard formulas. For rectangles, multiply the base by the height, and for triangles, use half the base times the height. By summing all these areas, we get an accurate measure of the total distance traveled during the time interval. This approach is useful for understanding motion without needing complex calculations, especially when velocity changes steadily. To estimate displacement during non-linear motion using a graph, we start by finding the value represented by one square on the grid. In this case, that would be the velocity multiplied by the time represented by that square, giving us the displacement per square. Next, we count all the full squares beneath the curve, since these represent the total displacement over time. For the squares partially covered by the curve, we estimate their combined area, often by grouping halves or other fractions together to make whole squares. Finally, the total number of squares, both full and estimated partials, is multiplied by the displacement value of one square. This method gives us a reasonable estimate of the total displacement when the motion isn't in a straight line. Next, let's focus on finding the acceleration of the sledge at 6 seconds using the velocity time graph. To do this, we draw a tangent line to the curve at t equals 6 seconds and then create a right-angled triangle by dropping perpendicular lines from the tangent. The acceleration is the gradient of this tangent, which means we calculate the change in velocity over the change in time. From the graph, the velocity changes by 7 meters per second over 8 seconds, so the acceleration at 6 seconds is 0.875 meters per second squared. It's also important to note that after about 10 seconds, the slope of the curve turns negative, indicating the sledge is decelerating or slowing down as it continues down the hill. This gives us a clear picture of how the sledge's speed changes throughout its motion. As we consider the motion of a ball dropped from a height and bouncing elastically, the velocity time graph shows a series of parallel lines with a constant negative slope equal to the acceleration due to gravity, reflecting the ball's upward and downward movement. At each bounce, the velocity abruptly changes direction, shown as sharp vertical lines on the graph. Meanwhile, the acceleration time graph remains mostly constant at negative gravity, except for brief spikes of large positive acceleration during each bounce, representing the rapid change in velocity as the ball hits the surface. Together, these graphs illustrate the nature of the ball's motion and acceleration during perfectly elastic bounces. To wrap up, think of motion not just as lines on a grid, but as a story told through geometry. By understanding gradients and areas, you can interpret the past, present, and future of any movement. For example, this train's journey can be broken down into its displacement over time, which shows how far it has traveled, its velocity over time, which tells us how fast it is moving at any moment, and its acceleration over time, revealing changes in speed. Each of these elements helps us decode the full story of motion in a clear, detailed way.